Is our universe just one possibility in an infinite sea of quantum potential? We are about to explore 30 of the most incredible theories explaining how everything began. You will discover ideas ranging from the profoundly beautiful to the utterly bizarre. What truly ignited the cosmos from nothing, and could our reality be nothing more than a sophisticated simulation? Which of these quantum origins feels the most real to you? The story of our universe often begins with a single, unfathomable point. This is the classic Big Bang singularity, a concept so extreme it defies all known physics. Imagine all the energy and matter in the entire cosmos, every galaxy, star, and planet, compressed into a volume smaller than a single atom. At that point, density and temperature become infinite, and the laws of space and time as we know them simply cease to function. From this state of ultimate extremity, our universe exploded into being, initiating the expansion we still observe today. We have compelling evidence for this event, most notably the cosmic microwave background radiation. This is the faint afterglow of that initial explosion, a cold whisper of heat that permeates all of space, acting as a fossilized snapshot of the universe in its fiery infancy. Yet for all its explanatory power, the Big Bang theory leaves us with profound and unsettling questions. What was the actual trigger that caused this singularity to erupt into a universe? What, if anything, could have existed before that moment when time itself began? The singularity is a boundary where our understanding ends, a cosmic dead end that forces us to look for a deeper, more fundamental set of rules. This is the very reason we must venture into the quantum realm, searching for answers in the strange and probabilistic world of the very small. That singularity, a point of infinite density, presents a profound puzzle. But what if the story did not truly begin there? A bold idea emerged to solve some of the Big Bang's deepest mysteries, a concept known as cosmic inflation. Proposed by physicist Alan Guth, this theory suggests that in the very first sliver of a second after the initial expansion, the universe underwent a growth spurt of unimaginable speed. For a fleeting moment, space itself expanded faster than the speed of light, stretching a subatomic speck of primordial universe into a vast cosmos. This incredible burst solves two major problems left by the classic Big Bang. First is the horizon problem. Look at the cosmic microwave background in opposite directions of the sky. It has the same temperature everywhere, which is very strange. How could two regions so far apart have reached the same temperature if there was never enough time for heat to travel between them? Inflation answers this by stating that these distant spots were once intimately close neighbors, inflated apart in an instant. The second puzzle is the flatness problem. Our universe appears remarkably flat on large scales, a very specific and unlikely condition. Inflation naturally forces the universe into this flat geometry, much like how blowing up a balloon makes its surface appear flatter and flatter. The engine for this hyper-expansion is thought to be a strange field that permeated the newborn cosmos called the inflaton field. As this field shifted its energy state, it released a colossal repulsive force, driving the exponential stretching of space itself. Think of the universe before inflation as a balloon covered in tiny, random wrinkles. During the inflationary burst, those microscopic quantum wrinkles were stretched to enormous sizes. They became the seeds for all the large-scale structure we see today, the gravitational blueprints for galaxies and clusters of galaxies. This elegant theory also makes a spectacular prediction. Such a violent stretching of spacetime should have created ripples in the fabric of the cosmos, primordial gravitational waves. Detecting these waves would be like hearing the faint echo of the universe's first moment. Our most sensitive observatories are listening for this whisper, a signal that could confirm our cosmic origin story was even more dramatic than we thought. Yet the concept of a single, definitive beginning is not the only possibility. What if our Big Bang was not a unique creation event, but merely one chapter in an endless cosmic story, a story with no true start and no final end? This is the core of the cyclic model, a vision of the universe as a perpetual motion machine of creation and destruction. Instead of a lone explosion from nothing, this theory proposes an infinite series of universes, each beginning with a Big Bang and ending in a big crunch, where all matter and energy collapse back upon themselves, only to rebound into a new expansion. This grand cycle elegantly sidesteps the troubling singularity problem, as each new universe is born not from an infinitely dense point of mystery, but from the energetic ashes of its predecessor. One of the most compelling versions of this idea lies within the framework of string theory, involving entities called brains. Imagine our entire universe, with all its 3 dimensions of space, is actually a vast floating membrane or brain, existing within a higher dimensional reality. In this picture, our cosmic cycle is driven by a slow, rhythmic dance. Another parallel brain drifts through this hidden space, and every trillion years or so, these 2 world sheets collide. That collision is not a destructive crash, but a creative one. The immense kinetic energy of the impact is converted directly into the hot, dense fireball of a new Big Bang, igniting a fresh universe within each brain. The universes then expand, evolve, and cool, eventually drifting apart, only to be drawn together once more for the next collision. Here, the mysterious force we call dark energy plays a crucial role. It is the agent that drives the universes apart after each collision, providing the necessary separation and time for structure to form, for galaxies to shine, and for life to possibly emerge before the gravitational pull ultimately wins out and draws everything back for the next cosmic rebirth. This leads to a truly staggering implication. If the universe is truly cyclic, then time itself may not be a linear arrow shooting from a single point of origin. Instead, it could be a vast, repeating loop. Every event, every star, every conscious thought might recur an infinite number of times across endless cycles. There is no ultimate beginning to ask about, and no final heat death to fear, only the eternal, rhythmic pulse of existence itself. But the idea of a cyclic cosmos is not the only challenge to our classical view. Another theory proposes that our perception of a 3-dimensional world is a magnificent illusion. This is the holographic principle, a concept so radical it suggests that all the information describing our universe, every star, every person, and every thought, is actually encoded on a distant, 2-dimensional surface like a cosmic DVD. We are not watching the movie, we are living inside the projection. To grasp this, think of an ordinary hologram, a flat, 2-dimensional piece of film, when illuminated with laser light, creates a stunning 3-dimensional image that you can walk around and look at from different angles. All the information needed to construct that full 3D experience is contained entirely on the 2D surface. The holographic principle applies this same logic to the entire cosmos. It posits that our reality, with its rich depth and volume, might be a similar projection. The information that makes up everything we see and feel could be stored on a vast spherical boundary that surrounds us, a surface at the very edge of the observable universe. The origins of this mind-bending idea are not in science fiction, but in the hard physics of black holes. When scientists studied the thermodynamics of these cosmic traps, they made a startling discovery. A black hole's entropy, which is a measure of its information content, is not proportional to its volume as you might expect. Instead, it is directly proportional to the surface area of its event horizon, the point of no return. This implies that all the information about whatever falls into a black hole is not lost within its 3-dimensional interior, but is somehow painted onto its 2-dimensional boundary. The holographic principle takes this black hole revelation and applies it to the universe as a whole. If this is true, then our daily experience of moving through a 3-dimensional world is a kind of deeply convincing trick. The solidity of the floor beneath your feet, the vast distances between galaxies, the very feeling of depth itself, all of it emerges from a complex code written on a distant, flat screen. This forces us to confront a profound question. What is more fundamental, the rich three-dimensional reality we inhabit, or the two-dimensional data that describes it? The holographic principle suggests that the data is the true reality, and our world is its magnificent, projected consequence, challenging the very nature of space, time, and what it means to be real. While the holographic principle reimagines reality as a projected image, another theory proposes that the very fabric of space and time is woven from something far more tangible. Loop quantum gravity offers a radical departure from the smooth, continuous spacetime of Einstein's general relativity. It suggests that space is not an empty stage but a dynamic fabric made of tiny, finite loops. These loops are the fundamental threads of reality, woven into a network so fine that it exists at the smallest possible scale, the Planck length. Picture the universe not as a smooth sheet, but as an incredibly intricate and ever-changing mesh, a spin foam where each connection represents a quantum of space. In this view, you cannot divide space infinitely. There is a smallest possible unit, a tiny grain of reality itself. This discrete nature of spacetime has a profound consequence for the origin of our universe. It completely eliminates the need for a singularity. Since space cannot be compressed to an infinitely dense point, the Big Bang was not a true beginning. Instead, loop quantum gravity describes a cosmic rebound known as the Big Bounce. Our expanding universe was born from the collapse of a previous cosmos. As that earlier universe contracted under its own gravity, it reached a point of maximum density, not infinity. The repulsive force generated by the quantum nature of spacetime itself became overwhelming, causing the universe to bounce back outward, initiating our own expansion. This transforms the cosmic story from a single, inexplicable explosion into a potentially endless cycle of renewal. The universe breathes in and out, with each bounce erasing much of the past but potentially leaving faint echoes in the cosmic background radiation. This granular structure of spacetime also addresses the troubling fate of information inside black holes. In this framework, the center of a black hole might not be a point of infinite density, but could instead connect to another region of spacetime through a cosmic bridge, a possibility that reshapes our understanding of the universe's most extreme environments. The fabric of reality may be woven from threads of pure vibration. String theory proposes that the most fundamental constituents of the universe are not point-like particles, but unimaginably tiny, one-dimensional loops of energy. Think of a guitar string. Pluck it one way and it produces a specific musical note. Pluck it with a different tension and you get a different note. In string theory, these fundamental strings are vibrating in a similar way. Each distinct vibration pattern, each unique resonant frequency, does not create a sound, but instead manifests as a different fundamental particle. One specific vibration corresponds to an electron, another to a quark, and still another to the photon, the particle of light. In this elegant framework, all the diverse matter and forces we observe are simply different notes on the same cosmic instrument, a symphony played on strings smaller than an atom. But for this symphony to have the rich complexity we observe, the strings cannot be vibrating in only the three spatial dimensions we experience. The mathematics of string theory requires extra dimensions of space, curled up into shapes so minute that we never perceive them directly. The specific geometry of these hidden dimensions determines the possible vibrational notes of the strings, which in turn dictates the laws of physics for that universe. This leads to one of the most profound implications of the theory, a concept known as the string theory landscape. Instead of one unique set of physical laws, the theory allows for a staggering number of possible solutions, each corresponding to a different stable configuration of those extra dimensions. This is not just a handful of variations, but a number so vast it dwarfs the count of all the atoms in the observable universe. Within this landscape, our entire cosmos could be just one tiny bubble in an infinite cosmic foam. Each bubble universe nucleates with its own random set of compactified dimensions, and therefore its own unique set of physical constants and laws. In most of these universes, the conditions would be wildly inhospitable. The strength of gravity might be too strong for atoms to form, or the nuclear forces too weak to ignite stars. We find ourselves in a universe with just the right rules for complexity and life, not because it is special or designed, but simply because it is one of the rare bubbles where such a delicate balance was possible. We are living in a cosmic habitat that allows for our existence, surrounded by an infinity of lifeless, alien realities. This vast multiverse emerges not from random chance, but from the fundamental physics of vibrating strings and their hidden dimensional landscapes, suggesting that our reality is just one possible melody in an endless symphony of existence. The violent embrace of two cosmic membranes could be the true spark of creation. This is the ekpyrotic universe, a dramatic variant of the cyclic model that replaces the fiery singularity with a collision in a higher dimensional reality. Picture our entire three-dimensional universe as a vast, flexible sheet, a brain floating within a hidden fourth dimension of space. Parallel to us drifts another universe, another brain, separated by an unimaginably small gap. The engine of creation is not a mysterious inflattened field, but pure kinetic energy. When these two world sheets are drawn together by gravity, they collide. That impact is our Big Bang. The immense energy of the collision is instantly converted into the hot, dense plasma of matter and radiation that would eventually coalesce into everything we see. This model elegantly avoids the problem of a singularity, as the universe is born not from an infinitely dense point, but from a well-defined energetic event. Like the brain collision model we discussed earlier, the ekpyrotic scenario is cyclic. After the collision, the brains bounce apart, the universe within them expands and cools, and then, over trillions of years, gravity pulls them back for another cosmic rebirth. But how does this theory explain the universe we observe today, specifically its large-scale structure and remarkable uniformity? During the slow, gentle approach before the collision, quantum fluctuations on the surfaces of the brains are stretched and amplified. These ripples become the seeds for all future structure, the gravitational fingerprints that would one day guide the formation of galaxies and clusters, all without requiring a period of hyper-fast inflation. This entire breathtaking process is deeply rooted in M-theory, a leading candidate for a unified theory of physics. M-theory proposes that the fundamental building blocks of reality are not just strings, but also higher dimensional membranes or brains. Our universe, in this view, is one such brain, and the ekpyrotic model is the story of its most consequential interaction. We are left to wonder if the entire history of our cosmos, from the first instant to the present day, is merely the aftermath of a single, shattering contact between worlds we cannot see. Perhaps the most humbling origin story suggests our entire cosmos is a cosmic free lunch. This is the theory of quantum fluctuation from nothing, an idea that pushes the boundary between physics and philosophy. It proposes that the universe spontaneously burst into existence from a perfect vacuum, an event requiring no external cause or prior creation. The mechanism for this seemingly impossible feat lies in one of quantum mechanics' most fundamental rules, the Heisenberg uncertainty principle. This principle states that on the tiniest scales there is an inherent fuzziness to reality. You cannot precisely know both the energy of a system and the exact time that energy is measured. This leads to a remarkable loophole. Empty space is never truly empty. Even in a perfect vacuum, pairs of virtual particles and their antiparticles can spontaneously blink into existence, borrowing energy from the void for an immeasurably brief moment before annihilating each other and repaying the debt. We have observed this effect indirectly in laboratories, a phenomenon known as the Casimir effect. Now, scale this quantum quirk up to an unimaginable degree. What if, in the primordial void, a quantum fluctuation occurred that was not a pair of particles, but an entire universe? The uncertainty principle would allow for such a massive borrowing of energy, provided it happened quickly enough. In this view, the Big Bang was the ultimate quantum event, a fluctuation so vast it created the very space-time and energy it momentarily borrowed. This forces us to redefine what we mean by nothing. The nothingness this theory describes is not a philosophical absolute nothing. It is the quantum vacuum, a seething sea of potentiality governed by probabilistic laws. It is a nothing that contains the latent potential for everything. The philosophical implications are staggering. If this theory is correct, the question why is there something rather than nothing might be based on a false premise. Something and nothing are not eternal opposites. The quantum vacuum, with its propensity for spontaneous creation, may be the ultimate ground of being, eternally giving birth to universes in an unending cascade of cosmic genesis. Our entire reality, with all its galaxies and life, could simply be one particularly successful fluctuation that avoided immediate collapse, a single bubble that grew into a cosmos. Stephen Hawking proposed a universe with no edge in time. His no-boundary proposal, developed with James Hartle, reimagines the very nature of the Big Bang. It suggests the universe did not erupt from a singular point of infinite density, but rather curved smoothly into existence from nothing. To understand this, think of our planet Earth. You can travel north forever, but you will never reach a boundary called north. You will eventually reach the North Pole, a point that is perfectly finite, yet it is not an edge. The North Pole is the beginning of your southward journey, not the end of the map. Hawking and Hartle applied this same logic to time itself. In their model, the beginning of the universe is like the North Pole of time. There is no boundary, no sharp edge where the laws of physics break down. The universe is simply finite, but without a definitive starting line. To achieve this smooth geometry, the theory employs a fascinating mathematical trick. It replaces real time with something called imaginary time. This is not time as we experience it, flowing from past to future. It is a different dimension used to round off the sharp point of the singularity. Imagine the universe's origin not as a sharp cone, but as a smooth, rounded shape like the cap of a shuttlecock. In this picture, the Big Bang is not a violent explosion from a point, but a gentle, continuous curving into being. The universe has a minimum size, but no boundary, no moment of creation where something was summoned from nothing. This elegant solution dissolves the troubling singularity, offering a vision of a self-contained cosmos that requires no external cause. It presents a profound question. Is our deep-seated intuition of a linear timeline with a definitive beginning just an illusion, a shadow cast by a more complex, seamless reality we cannot directly perceive? Death is not an ending, but a transformation. Roger Penrose's conformal cyclic cosmology proposes an eternal return so profound it redefines the very concepts of birth and death for the cosmos. In this controversial vision, our universe is merely one aeon in an infinite chain, each beginning with a hot Big Bang and ending in a cold, empty expanse. The key to this endless cycle lies in a process called conformal rescaling, a mathematical transformation that allows the universe to forget its scale. In the far, far future, when all matter has decayed and black holes have evaporated, the universe becomes an endless, featureless sea of low-energy radiation. There is nothing left but light, and with no particles to measure distance or time, the concepts of large and small, near and far become meaningless. This vast, cold, empty end state is mathematically identical to the hot, dense, tiny beginning of a new Big Bang. The end of one eon seamlessly becomes the start of the next, not through a violent collision or a bounce, but through a graceful reset of the cosmic scale. Think of a camera lens zooming out from a single grain of sand until it becomes a microscopic speck in a vast desert. Then the lens refocuses, and that same speck becomes the entire world for a new beginning. The universe does this to itself. To support this radical idea, Penrose and his collaborators have searched for fossilized evidence from a previous eon. They propose that the titanic explosions of supermassive black holes from our universe's predecessor left faint, circular imprints in the cosmic microwave background, the oldest light we can see. These features, called Hawking points, are rings of slightly raised temperature that should not exist in a standard single-cycle universe. Their tentative detection is the subject of intense debate, a potential ghost image from a cosmos that existed before our own. If conformal cyclic cosmology is correct, then our entire cosmic history, from the first stars to the last dying ember, is destined to be washed away and reborn, an endless, timeless loop where every ending is a new beginning written in the same fundamental code. Our reality might be a sophisticated digital construct. The simulation hypothesis presents a startling possibility that everything we perceive as the universe is nothing more than an elaborate program running on a computer of unimaginable power in a higher realm of existence. The core argument for this idea rests not on finding glitches in our world, but on a simple, logical probability. If a civilization advances far enough, it is reasonable to assume it would develop the capability to run incredibly detailed simulations of its own past or of entire fictional worlds. These ancestor simulations would be so complex that the simulated beings inside them would be fully conscious, believing their reality to be authentic. Now, if such a civilization could run even one such simulation, it is statistically likely that it would run many, perhaps millions or billions. Therefore, the number of simulated minds would vastly outnumber the number of original, base reality minds. If that is the case, what are the odds that we are among the rare originals, and not one of the astronomical number of simulations? It is far more probable that we are living inside one of these countless digital worlds. This logic turns our sense of identity on its head, suggesting we are more likely to be advanced software than biological pioneers. Intriguingly, the fundamental laws of physics seem to offer clues that support this technological creation story. Our universe is not a perfectly smooth continuum. Space, time, and energy all appear to be quantized, meaning they come in discrete, indivisible packets. There is a smallest possible unit of distance, the Planck length, and a smallest possible unit of time, the Planck time. This pixelation of reality is exactly what you would expect from a massive computation. A simulation would have a finite resolution to manage its processing load, a fundamental limit to how fine the details can get, just like the pixels on a screen. The fixed speed of light could be seen as the processing speed limit of the cosmic computer, ensuring that no part of the simulation updates too quickly and causes a system crash. Even the strange rules of quantum mechanics, with their probabilities and uncertainties, resemble the optimized routines of a video game engine, which only renders the details of a scene when a player is looking at it. In this modern Genesis story, the Big Bang was not a physical explosion, but the moment the simulation was booted up, the laws of physics are simply the underlying code, the operating system of our existence. This forces us to confront a deeply philosophical question. If we are in a simulation, does that make our lives, our loves, and our struggles any less real? Or does the experience of consciousness itself become the only reality that truly matters? The universe may have needed an audience to truly come into being. This is the heart of the participatory anthropic principle, a radical proposal by physicist John Archibald Wheeler that places consciousness at the very center of cosmic existence. Wheeler was deeply influenced by the strangest aspect of quantum mechanics, the fact that a particle does not have a definite position or state until it is measured. In his famous delayed choice thought experiment, he showed that a decision made by an observer in the present could seemingly influence the past behavior of a particle. This suggests that reality is not a fixed, pre-recorded movie, but is instead being generated moment by moment through the act of observation. Wheeler took this quantum weirdness to its ultimate, logical extreme. He proposed that the universe could only achieve a concrete, tangible reality once it had produced conscious observers to look back upon it and, in a very real sense, bring it into being. In this view, we are not just passive inhabitants of a finished cosmos. We are active participants in its creation, closing a cosmic loop that stretches from the Big Bang to the present day. This leads to a profound resolution of the universe's apparent fine-tuning. The fundamental constants of nature seem perfectly calibrated to allow for stars, planets, and life. The participatory anthropic principle offers a startling answer to why this is so. The universe is tuned for life because life is a prerequisite for the universe to become real. We are not here because the universe is special. The universe is special because we are here to observe it. This idea blurs the line between the created and the creator in a way no other theory does. We are not gods, but our collective act of observation is an essential part of the cosmic machinery, transforming a fog of quantum potential into the solid world we experience. Our search for the origin of everything becomes a search that ultimately includes ourselves, as if the universe had to invent the eye to finally see itself. Every black hole might contain an entire cosmos. This is the startling premise of black hole cosmology, a theory that reimagines our universe as the interior of a colossal black hole residing within a much larger parent universe. The connection lies in a profound similarity between two of physics' most extreme events. The Big Bang began as a state of unimaginable density and temperature, a singularity from which space and time erupted. A black hole, in its final state of gravitational collapse, also culminates in a singularity of infinite density. What if these are not two different phenomena, but the same event viewed from opposite sides? In this picture, the Big Bang was the moment our universe was born inside the event horizon of a black hole belonging to another, older reality. The event horizon is the point of no return, the boundary where the parent universe's gravity becomes so strong that not even light can escape. From our perspective inside, this horizon is not a wall we are trapped behind, but the very edge of our expanding observable universe. The initial rapid expansion we call inflation could be explained by the intense, focused energy of the material as it was crushed into the new singularity. This leads to a fractal vision of existence, a cosmic Russian nesting doll of unimaginable scale. Every single black hole that forms in our universe could, in its impenetrable interior, be the seed for an entirely new cosmos, bursting into life with its own Big Bang. Those daughter universes would then give birth to their own black holes, each spawning another generation of reality in an unending cascade of creation. Our universe, with its hundreds of billions of galaxies, each containing billions of stars, becomes a fertile breeding ground for countless new worlds. This theory also offers a compelling explanation for the specific laws of physics we observe. The fundamental constants, like the strength of gravity or the mass of an electron, might not be arbitrary. They could be inherited properties passed down from the specific conditions of our parent black hole. Just as a child inherits genetic traits from its parents, our cosmos may operate under rules that were set in stone during its violent birth in another reality. We live in a universe with these particular laws because only a black hole with these specific properties could have given rise to us. This transforms black holes from cosmic tombstones into cosmic wombs, suggesting that the death of a star in one universe is the genesis of an entire reality in another. Our universe may have been born from the death of another. The Big Bounce theory offers a breathtaking alternative to a singular beginning, replacing the mysterious Big Bang singularity with a cosmic rebound. This idea finds its strongest foundation in loop quantum gravity, where the fabric of space itself is not smooth and continuous but woven from a fine mesh of indivisible loops. Because space is quantized, it cannot be compressed into an infinitely dense point. There is a smallest possible size, a fundamental grain of reality. This changes everything about the moment of origin. Instead of a universe erupting from an impossible singularity, imagine a previous cosmos gracefully aging, its expansion slowing, halting, and then reversing into a great contraction. All the galaxies would fall back toward each other, space itself squeezing tighter and tighter. But as it approaches the maximum possible density allowed by the quantum grain of space, a tremendous repulsive force generated by the quantum nature of gravity itself kicks in. This is not a collision or an explosion, but a fundamental pushback from the geometry of reality. The universe reaches a point of supreme density and then bounces, like a ball compressed to its limit and springing back outward. That rebound is our Big Bang, the start of our current cycle of expansion. This cyclical model elegantly erases the need for a definitive beginning. What existed before the bounce was simply another phase of the universe, a contracting era that may have itself been preceded by an infinite number of such cycles. Time becomes a series of cosmic heartbeats, with each cycle potentially lasting trillions of years. While each bounce likely erases most of the specific information from the previous universe, some physicists speculate that subtle imprints might survive, hidden in the cosmic microwave background or in the very gravitational wave fabric of spacetime. The Big Bounce transforms our story from a one-time creation event into a potentially eternal rhythm of renewal, where every ending is merely a prelude to a new beginning. Eternal inflation offers a dramatic answer to why our universe appears so finely tuned for life. The theory suggests that the explosive expansion we call cosmic inflation never truly ended everywhere. Instead, it stopped in our local region, creating our familiar universe, but continues unabated in the wider cosmic landscape. Imagine a vast, bubbling cauldron of space forever boiling. Each time a bubble forms in this seething foam, inflation stops inside it, and that bubble becomes a stable pocket universe with its own random set of physical laws. Our entire cosmos is just one such bubble among an infinite and ever-growing number. The constants of nature we take for granted, the strength of gravity, the mass of an electron, are not universal laws handed down from on high. They are simply the local bylaws of our particular bubble, a fortunate roll of the cosmic dice. In the vast majority of these pocket universes, the physics is wildly different and completely inhospitable. Some might have gravity so strong they instantly collapse back into nothing, while others might have forces too weak to ever form atoms. We do not live in a special universe designed for us. We simply find ourselves in one of the rare bubbles where the numbers came out right, a cosmic habitat where stars could ignite and planets could form. This endless proliferation of realities transforms the fine-tuning problem from a profound mystery into a simple question of probability. With an infinite number of tries, every possible combination of physical constants will eventually appear somewhere. Our existence is not a miracle, but a statistical inevitability in a multiverse without end. Space-time may not be a smooth, flowing river, but a chain of distinct moments. Causal set theory proposes a universe built not from a fabric, but from a vast collection of individual events like grains of sand. Each event is a fundamental point of happening, and the only thing that truly matters is their causal relationship, which event can influence another. This creates a cosmic web of cause and effect, a minimalist architecture for reality where the order of events is everything. The universe, in this view, grows not by stretching, but by the continual birth of new events, each one finding its place in the ever-expanding network of causality. From this sparse, discrete foundation, something miraculous emerges. The smooth, continuous spacetime described by Einstein's general relativity with its warps and curves is not fundamental. It is an illusion, a large-scale average that arises from the immense number of causal connections, much like a smooth digital image emerges from the coarse grid of individual pixels when you view it from a distance. The force of gravity itself and the very geometry of the cosmos could be a consequence of this underlying combinatorial structure. This theory offers a profoundly simple origin story. The cosmos began not with a bang, but with a single seed event. From that first cause, new events were added, one after another, each new point in the network creating new possibilities for future causes and their effects, steadily building up the rich history of our universe from pure, unadorned causality. The entire four-dimensional tapestry of spacetime, with every past and future moment, is just a way of looking at this immense, growing causal network. Time itself may be a phantom, a side effect of the universe's relentless slide into disorder. The thermal time hypothesis proposes that time is not a fundamental feature of reality but an emergent property, born from the thermodynamic gradient of our cosmos. Our deep-seated feeling of a flowing present, a past we remember, and a future yet to come could all be a consequence of entropy. This is the measure of disorder in a system, a quantity that always increases, giving the universe an irreversible direction. Think of an ice cube melting in a warm room. The organized, crystalline structure of the ice dissolves into a puddle of disordered water molecules. You never see the puddle spontaneously refreeze into a perfect cube on its own. That one-way street from order to chaos is the arrow of time, and it is powered by the universe's own low entropy beginning. The Big Bang was a state of extraordinarily low entropy, an impossibly ordered and uniform starting point. From that pristine initial condition, the cosmos could only evolve in one direction, toward higher and higher states of disorder. This ever-increasing entropy is what creates the thermodynamic gradient that our brains interpret as the passage of time. Without this cosmic imbalance, the very concepts of cause and effect would lose their meaning. The thermal time hypothesis takes this a step further. It suggests that the smooth, continuous time described by physics is not a primary ingredient of the universe. Instead, it is a statistical illusion generated by the microscopic, random motions of countless particles all moving toward greater disorder. The flow of time is the story of the universe forgetting its original, highly ordered state. This leads to a profound connection between the origin of everything and our own conscious experience. The beginning of the universe was not just the start of space and matter, but the very moment the clock started ticking. The low-entropy Big Bang gave time its arrow and its apparent flow. We perceive time because we are products of this cosmic gradient. Our memories and thoughts are processes that rely on increasing entropy. If the universe ever reached a state of maximum entropy, a featureless heat death where no further change was possible, would time simply stop? From the perspective of this theory, the answer is yes. Without a gradient, without change, the emergent phenomenon we call time would cease to have any meaning. Our reality is not unfolding on the stage of time. Time is the story of the unfolding itself. The universe may be written in the language of mathematics, but its source code could be a vast and intricate matrix. This is not the simulated reality of science fiction, but a profound physical theory known, appropriately, as matrix theory. It stands as a specific and powerful formulation of M-theory, proposing that the fundamental description of our 11-dimensional reality is not made of strings or brains, but is instead a massive quantum mechanical matrix. Imagine a cosmic spreadsheet of unimaginable complexity, where each cell is not a simple number but a complex mathematical object that can interact and evolve. The positions and properties of every fundamental particle, from the quarks in an atom to the photons crossing the void, are described by the values within this grand matrix. The dynamics of the cosmos, the very unfolding of space-time and the dance of forces, are the result of this matrix calculating itself following the strict rules of quantum mechanics. In this framework, the force of gravity and the other fundamental interactions are not separate phenomena. They emerge from the same underlying matrix algebra, offering a potential path to the long-sought theory of everything, a single mathematical system that can describe the universe from the smallest scale to the largest. This leads to a radical reimagining of the Big Bang. If reality is fundamentally a matrix, then the beginning was not a geometric event in a pre-existing space. It was a computational transition. The Big Bang becomes the moment this cosmic matrix underwent a profound phase change, a shift in its fundamental state that generated the dimensions of space and the flow of time as emergent properties. From a timeless, spaceless state of pure information, the dynamics of the matrix crystallized into the geometric universe we recognize. The initial rapid expansion of inflation can be seen as a specific solution within this matrix model, a natural outcome of its early evolution. We are left to wonder if the three-dimensional stage we inhabit is merely a dominant, stable vibration mode of this deeper mathematical reality, a persistent pattern in the cosmic data that gives us the consistent illusion of a continuous world. Space and time feel like the unshakable stage upon which the universe performs, yet this stage itself might be the grandest illusion of all. The emergent universe theory proposes that our four-dimensional reality is not fundamental, but a secondary phenomenon that crystallizes from a deeper, more primitive layer of existence. This underlying reality would not be made of things located in space or events happening in time, because space and time as we know them would not yet exist. Think of how temperature emerges from the frantic, chaotic motion of countless atoms. A single atom does not have a temperature, it only has kinetic energy. The concept of temperature only makes sense when you have a vast collection of particles, their average motion creating the emergent property we can measure with a thermometer. In the same way, the smooth, continuous flow of time and the three-dimensional expanse of space could be collective behaviors arising from a vast network of quantum information or relationships operating at a level far below our perception. This quantum substrate would be a realm of pure connection, where the only things that are real are the relationships between fundamental components. The geometry of space-time and the force of gravity would not be primary forces, but would naturally bubble up from the complex dynamics of this network, much like the flow of a liquid emerges from the collective interactions of its molecules. This completely redefines the origin of everything. The Big Bang was not an explosion that happened in space and time. It was the moment, or more likely the process, through which space and time themselves precipitated into being from that formless, pre-geometric quantum state. The universe did not begin in a void. It began as the void began to take on the familiar properties of geometry and causality. The initial singularity is no longer a point of infinite density within an existing spacetime, but rather the boundary where spacetime itself first condensed. This transforms the hunt for the universe's origin from a search for a first cause in time to a search for the fundamental rules that govern a timeless, spaceless network of information. What we perceive as the relentless forward march of time could simply be our limited, emergent perspective on a much more static, eternal reality where every relationship is simply defined. Our journey from the past into the future might be as illusory as a movie where the entire film exists at once, but we only experience it frame by frame. A universe fine-tuned for life might simply be a side effect of a much darker imperative. Lee Smolin's theory of cosmological natural selection proposes a truly cosmic form of evolution, where universes do not just exist, they reproduce. In this startling vision, every black hole is a potential seed for a new cosmos. When a star collapses into a black hole, the singularity at its heart is not an end. It is a gateway, a moment of extreme conditions where the very laws of physics are reborn. The new universe that inflates from this gateway does not inherit an identical copy of its parent's physical constants. Instead, those fundamental numbers, like the strength of gravity or the mass of an electron, undergo a slight random mutation. This is the cosmic equivalent of a genetic variation. Now, apply the ruthless logic of natural selection to this multiverse of reproducing universes. Which universes will be the most successful, producing the greatest number of offspring? They will be the ones most effective at creating black holes, a universe where stars form easily, live fiery lives, and collapse dramatically into black holes will be incredibly prolific. Its mutated constants will be passed on to a vast number of daughter universes, a universe with constants that prevent star formation, or that cause matter to be too stable, will be a dead end, a cosmic evolutionary failure. Our own universe, with its hundreds of billions of galaxies, each brimming with black holes, is not just habitable, it is incredibly fertile. The very laws that allow for carbon-based life and conscious observers are the same laws that efficiently forge stellar graveyards. The fact that our cosmos seems perfectly tuned for life could be a fortunate byproduct of it being perfectly tuned for black hole production. We are not the purpose of the universe. We are living in a universe that won the cosmic Darwinian lottery by being exceptionally good at cosmic death and rebirth. A quantum handshake across time could be the true foundation of reality. The transactional interpretation of quantum mechanics proposed by physicist John Cramer offers a radical solution to the infamous measurement problem. In the standard view, a particle exists as a wave of probability until it is observed, at which point it mysteriously collapses into a definite location. The transactional interpretation eliminates this strange collapse by introducing a breathtaking symmetry. It suggests that when a particle is measured, it does not just send a wave forward in time. It also sends an echo backward in time, an advanced wave that travels from the future detection event into the past. The ordinary wave moving forward and its time-reversed echo meet and reinforce each other, creating a stable handshake, a transaction across time. This completed transaction is what we perceive as a real, definite event in the present. The particle is only truly real when its past and future have come to an agreement. Apply this extraordinary idea to the origin of everything. The Big Bang sent a colossal alpha wave forward through time, a wave of pure potentiality containing every possible future for the universe. Billions of years later, a specific future state, perhaps one containing conscious observers or a final, definitive configuration, sent a confirmation wave backward through time. This advanced wave, traveling from the cosmic end to the very beginning, completed the transaction. Our universe became concretely real only when its ultimate future reached back and shook hands with its birth. In this view, the Big Bang was not a one-time event. It was an offer that needed a future confirmation to become binding. The universe's beginning and its end are not separate moments on a timeline. They are inextricably linked in a single, timeless loop of causation, a self-consistent agreement written into the fabric of existence. The entire cosmic history, from the first star to the last thought, was solidified by this mutual confirmation between Alpha and Omega. We are living inside that confirmed transaction, in the reality that was chosen when the end called out to the beginning and found an answer. The entire cosmos could be a perfect balance sheet, its total energy precisely zero. This is the startling premise of the zero-energy universe theory, a concept that frames existence as the ultimate free lunch. All the stars, galaxies, and planets represent an enormous amount of positive energy. But this is only half of the cosmic equation. Bound to all that matter and light is the negative energy stored in the gravitational field. Gravity is an attractive force, and it takes positive energy to pull objects apart against its pull. Think of it like digging a hole. The pile of dirt you create has positive mass, but the hole itself represents a negative, an absence. In the cosmic ledger, the positive energy of all the mass in the universe is exactly cancelled out by the negative gravitational energy binding it together. The sum total is nothing. This elegant cancellation is not just a curious coincidence. It provides a profound answer to one of the oldest questions: why is there something rather than nothing? If the universe truly has zero net energy, then it could have popped into existence from a perfect vacuum without violating the sacred law of energy conservation. No energy needed to be created because the final balance was always zero. The Big Bang, in this view, was not an explosion that required a colossal input of power. It was a fluctuation that created equal parts something and nothing, a symmetrical blossoming of positive and negative that perfectly offset each other from the very first moment. Our magnificent, sprawling universe, in its most fundamental accounting, may cost absolutely nothing at all. Our universe may have been encoded on a two-dimensional screen at the beginning of time. The holographic Big Bang theory merges the stunning implications of the holographic principle with our cosmic origin story, proposing that the Big Bang was not a fiery explosion in 3 dimensions, but a quantum information processing event on a vast primordial surface. In this model, the initial singularity, that point of infinite density where physics breaks down, never actually existed. Instead, the entire cosmos began as a shimmering, hot, and incredibly dense hologram. All the information needed to describe every particle, every force, and the very space-time of our universe was compressed onto this two-dimensional boundary. Then, as this holographic surface cooled and evolved, the information was projected inward, giving rise to the full 3-dimensional reality we experience today. It is as if the universe booted up from a cosmic hard drive, with the 3-dimensional world we inhabit being the fully rendered output. This framework elegantly resolves the problem of the singularity, because the messy, infinite conditions are smoothed out on the 2-dimensional surface where the laws of quantum physics still hold sway. The moment of creation transforms from a violent geometric rupture into a phase transition, a shift from a 2-dimensional state of pure information to a 3-dimensional state of emergent geometry and matter. The initial rapid expansion of inflation can be understood as this projection process stabilizing and unfolding. We are left to wonder if the entire history of the cosmos, from the first instant to the present day, is simply the playback of a cosmic movie that was encoded on that initial 2-dimensional screen, a story written in the language of quantum bits that we are only now learning to read. A perfect cosmic symmetry could demand a twin for our universe. The laws of physics appear to be almost perfectly symmetric under a combined operation known as CPT. This stands for charge parity and time. Charge conjugation means swapping every particle with its antiparticle. Parity reversal is like looking at the universe in a mirror, flipping left and right. And time reversal means running the clock backward. Our universe is not perfectly symmetric under any one of these operations alone, but physicists believe the combined operation of all 3, C, P, and T together, must be a fundamental symmetry of nature. This principle suggests that if you took our entire universe, replaced every particle with its antiparticle, viewed it in a mirror, and ran time backward, the resulting universe would obey exactly the same physical laws as our own. This profound symmetry leads to a staggering possibility. For this cosmic balance to hold true, our universe might not be alone. There could be a mirror universe, a perfect CPT transformed twin that was born alongside our own at the moment of the Big Bang. From our perspective, this twin would evolve backward in time. While we move from the Big Bang toward the future, this mirror cosmos moves from the future back toward the Big Bang. It is not a separate creation, but the other half of a single, symmetric reality. In that universe, time flows in the opposite direction. What we call the future is their past, and our past is their future. An observer in that mirror universe would perceive their time as moving forward, just as we do, and they would see us as the ones moving backward. This is not science fiction, but a direct consequence of demanding that the most fundamental laws of physics remain balanced. This mirror cosmos would be almost entirely separate from our own, its particles unable to interact with ours in any normal way, yet it could be the hidden key to one of our greatest mysteries, dark matter. The invisible substance that holds galaxies together might simply be the ordinary stars and planets of that mirror universe, made from mirror atoms and mirror light, whose gravitational influence is the only way it can leak into our reality. The very arrow of time, the reason we remember the past and not the future, could also find an explanation here. The low entropy beginning of our universe might be connected to the low entropy end of the mirror universe, creating a single, symmetric system where order is preserved across both timelines. We are living in just one half of a perfectly balanced cosmic equation, forever linked to a reflection we can never directly see. Space-time itself may have frozen into its current form from a more fundamental chaos. Quantum gravity proposes a universe where space is not a primary ingredient of reality, but a secondary structure that congealed as the cosmos cooled. In its earliest moments, the universe was not a tiny point in space. It was a seething, dynamic network of quantum relationships, a vast graph of interconnected nodes. Each node represented a fundamental bit of information, and the connections between them were in a state of constant, frantic change. In this primordial state, there was no such thing as distance or dimension. Every node was effectively connected to every other node, creating a state of ultimate proximity and chaos. The concepts of here and there were meaningless because everything was, in a quantum sense, everywhere at once. This highly connected, soupy state is what we might identify as the moment of the Big Bang. It was not an explosion in space, but the starting condition of the network itself. Then, as the universe expanded and cooled, a cosmic phase transition occurred, much like water freezing into ice. The frenetic connections in the graph began to stabilize. A new, lower energy state emerged where each quantum bit formed strong, stable links only with its immediate neighbors. This sudden organization of the graph is what created the familiar properties of space. The stable pattern of local connections gave rise to the three dimensions we move through, and the consistent speed at which information could travel across this newly formed lattice became the speed of light. The very geometry of space-time, with its ability to curve and warp, is a direct reflection of the underlying graph structure. A dense region of the graph would manifest as a gravitational well, while a sparse region would correspond to empty space. This theory completely rewrites the origin story of everything. The Big Bang was not the beginning of space and time, but the moment the network began its transition from a hot, disordered state to a cold, ordered one, crystallizing the stage upon which the cosmic drama would later play out. We are living inside that frozen graph, experiencing its stable, local connections as the solid, continuous reality of the world around us. The rules of physics feel so permanent, so absolute. But what if they are merely the frozen artifacts of a more fluid and chaotic past? This is the protean universe theory, a vision of a cosmos that forged its own laws as it grew. In the first searing moments after the Big Bang, the universe was an unimaginable inferno. Under such extreme heat and density, the fundamental forces we know today were not separate entities. The electromagnetic force, the weak nuclear force, the strong nuclear force, and even gravity were likely fused into a single, unified superforce. In this primordial state, there was no distinction between a quark and a lepton, between matter and energy. Everything existed in a symmetrical, undifferentiated soup, a state of pure potential where the very concepts of different particles and forces had no meaning. As the universe rapidly expanded and cooled, it underwent a series of cosmic phase transitions, much like steam condensing into water and then water freezing into ice. At each critical temperature threshold, a piece of this perfect symmetry broke. With each broken symmetry, a fundamental force peeled away from the unified whole, acquiring its own unique identity and character. The strong force became locked within atomic nuclei, while the electromagnetic and weak forces parted ways. The particles themselves, the quarks and electrons, crystallized out of this energetic broth, gaining the specific masses and charges we measure today. The universe did not simply unfold according to a pre-written rulebook. It was actively writing that rulebook as it cooled, its fundamental constants solidifying from a spectrum of possibilities. The specific values we observe for the electron's mass or the strength of gravity might not be the only possible outcomes. They could be the frozen accidents of our cosmic cooling process, the particular configuration that happened to lock in as the temperature dropped below a critical point. In another universe, or even in a different region of our own, the constants could have frozen differently, leading to a reality with entirely different physics. This idea transforms our understanding of fine-tuning. The universe is not necessarily fine-tuned for life from the outset. Instead, life emerged in a universe that happened to cool into a set of laws that allowed for complexity. We are not the predetermined goal of creation, but the lucky beneficiaries of a random cosmic freeze. The protein universe was a shape-shifter, and we are living in the particular form it settled into, a form that just so happened to make our existence possible. Perhaps our own consciousness is the least likely thing in the cosmos. This is the unsettling core of the Boltzmann brain paradox, a thought experiment that uses the logic of probability to challenge our most fundamental assumption that we are real beings in a real universe. It begins with a simple thermodynamic fact: the universe is a system sliding from order into disorder. Yet here we are, surrounded by immense order, from the structured orbits of planets to the complex patterns of life. In an eternal and random cosmos, fluctuations happen. Given enough time, even the most improbable events will occur by chance alone. A random jostling of atoms could, in theory, spontaneously assemble a fully formed, self-aware brain, complete with false memories of a past that never existed. According to pure probability, the energy required to conjure a single, disembodied brain from the quantum foam is vastly less than the energy needed to create an entire, ordered universe spanning billions of light years. Therefore, in a truly eternal and random reality, the number of these lone, fluctuating brains should overwhelmingly outnumber the number of coherent universes with conscious observers like us. The paradox hits with full force. If our cosmological models point toward an eternal, chaotic void, then you are statistically far more likely to be a momentary Boltzmann brain, hallucinating a universe from a void, than a person living in a long-lasting, ordered cosmos. This is not a theory of creation, but a devastating critique. It forces us to ask a terrifying question. How can we trust any of our observations about the cosmos if the simplest explanation is that we just popped into existence a moment ago, with all our memories and the entire universe neatly pre-packaged inside our solitary, floating mind? This paradox puts immense pressure on any cosmological model that suggests an eternal, infinite, or random beginning. It implies that our universe must have a very specific starting condition, one that makes the existence of an ordered reality like ours more probable than the spontaneous generation of lonely minds. Our very sense of a continuous past may be the most powerful evidence that we are not just fleeting flashes in an eternal dark. A hidden symmetry could be the key to the universe's very first moments. Supersymmetry is a beautiful yet unproven theory that proposes a deep and fundamental partnership at the heart of reality. For every known particle of matter, like quarks and electrons, there should exist a superpartner, a ghostly twin that is a force carrier. And for every known force carrier, like the photon, there should be a superpartner that is a particle of matter. This would mean the electron would be paired with a selectron and the quark with a squark. The photon would have a photino, and the graviton, the hypothetical particle of gravity, would be matched with a gravitino. In this perfectly symmetric state, the sharp distinction between the building blocks of material and the messengers of force completely vanishes, revealing a more elegant and unified cosmos. In the extreme energies of the Big Bang, this symmetry would have been perfect. The universe was a much simpler place where matter and force were two sides of the same coin. This pristine state is crucial because it solves one of the biggest puzzles in particle physics, the hierarchy problem. The Higgs boson, the particle that gives others mass, is incredibly light, and physicists cannot explain why it is not driven to an enormous mass by quantum fluctuations. Supersymmetry provides a graceful solution, as the quantum contributions from matter particles and their superpartners would perfectly cancel each other out, naturally protecting the Higgs's delicate mass. This cancellation also allows for the grand unification of forces, suggesting that the electromagnetic, weak, and strong forces were truly one single force in the early universe's supreme heat. But we do not live in this perfectly balanced world today. As the universe expanded and cooled, this supreme symmetry broke. The superpartners, if they exist, became incredibly massive, too heavy for our current particle colliders to detect. We are left with the asymmetric, broken world we see, a world where matter and force are clearly separate, yet the ghost of that symmetry might be all around us. One of these heavy, stable superpartners, likely the neutralino, is a prime candidate for the mysterious substance we call dark matter. Invisible and barely interacting, it could be the hidden bulk of the cosmos, a direct relic from that more symmetric age. The search for these particles is a hunt for the lost symmetry of creation, an echo from a time when the universe was a more orderly and mathematically beautiful place. The final fate of our universe might be one of absolute, violent disintegration. A particular form of dark energy, known as phantom energy, presents a scenario far more terrifying than a slow, cold heat death. If this phantom energy exists, its defining trait is an equation of state with a value less than -1. This is not just a subtle mathematical difference. It means that the repulsive force accelerating the universe's expansion does not remain constant, but grows stronger over time, becoming infinitely powerful. The consequence of this escalating force is an event known as the Big Rip. First, the phantom energy would overcome the gravitational glue holding galaxy clusters together, sending them flying into an ever-darkening void. Next, it would tear apart individual galaxies. Then, as the force intensifies, it would rip stars from their solar systems. In the final moments, the phantom energy would become so overwhelming that it would shred atoms, nuclei, and even the very fabric of spacetime itself. The universe would end not with a whimper, but with a catastrophic, fundamental dissolution of reality. Yet from this uttermost chaos, a new beginning could emerge. Some theoretical models suggest that the Big Rip is not a true end, but a cosmic reset button of unimaginable violence. The point of infinite disruption, where spacetime itself is torn asunder, could create conditions similar to the initial singularity of a new Big Bang. In this view, the ashes of total disintegration are not nothingness, but a seething, energetic state from which a new universe can spontaneously inflate. The death of one reality becomes the chaotic, violent labor pains for the birth of another. This transforms the phantom energy from an agent of pure destruction into a cosmic catalyst for renewal, forcing us to wonder if the most ultimate end our universe can face is merely the prelude to another chapter in an eternal story of destruction and creation. The ultimate goal of physics is a single, elegant equation, a theory of everything. This final theory would weave the fabric of spacetime described by general relativity together with the strange probabilities of quantum mechanics, creating a single, seamless picture of reality from the largest cosmic scales to the smallest subatomic realms. Such a framework would not just describe how the universe behaves, but why it exists at all. It would point to a first cause that requires no prior cause, a self-contained logical necessity. Imagine a mathematical structure so profound and complete that its very existence demands physical manifestation. Our universe, with all its galaxies, forces, and life, would not be a random accident, but an inevitable consequence of this pure, abstract truth. The Big Bang would then be seen not as the beginning, but as the moment this perfect mathematical structure unfolded into the dimensions of space and time we inhabit. In this vision, we are not living in a universe that happened to have the right rules. We are living within the only possible set of rules, a cosmic equation solving for itself. The search for this final theory is the greatest detective story in science, a quest to read the original cosmic blueprint and finally understand why there is something rather than nothing. From bouncing universes to holographic projections and cosmic simulations, we have journeyed across 30 breathtaking visions of how everything began. Each theory offers a unique window into the profound mystery of our existence, challenging our most basic assumptions about reality, time, and our own place in the cosmos. This grand quest to understand our quantum origins is more than a scientific endeavor. It is one of humanity's greatest adventures, a testament to our insatiable curiosity and our courage to ask the biggest questions. We stand at the edge of the known, peering into the void, searching for the story that feels like home. So tell us, which of these theories reshaped your understanding of reality? Which origin story left you in awe? Let us know in the comments, share your thoughts, and if your mind is reeling from these possibilities, be sure to like this video and subscribe for more journeys to the edge of understanding. The conversation about the nature of reality is just beginning.